And sharing screen. All right. So hope you see the screen that I'm sharing with you on the textbooks. So we start with the chapter 12. This is derivative of for more functions or functions of two or more variables. So mostly two variables. Okay. So we now write we call this function actually a real valued functions of two variables. Okay. So each x and y, so two inputs, x and y, and one output, real output. Okay, we call it usually z. Okay, so this is kind of expressions. You can have a various expressions. Okay, now the domain lies in the xy axis. Domain D is the domain of the functions. So it's part of the xy axis. Okay, the range is in the z. Okay, x and y the independent variables and z dependent variables. We'll do some details later on. This is just a example of a functions. Uh, this is a rational forms. And so in the numerators, you have square root of y minus x squared, okay, over x squared plus y minus 1 squared. Okay, so you see the restrictions here is the square root, because on the square root, inside the square root, you gotta have a non-negative, cannot be negative. So meaning that y minus x squared should be uh, at least 0. Okay, so y should be less than x squared. Okay, and also here the numerator, sorry, numerator, denominator cannot be 0. So x cannot be 0 with y equals 1. Okay, so the natural domain for this is figure 2 like this. So here, sorry, I should say this, y must be bigger than x squared. So this is the area where the region where y is bigger than x squared. Okay, and you have to exclude also the point 0, 1, because uh, if you substitute 0, 1, x equals 0, y equals 1, then it makes the denominator 0. Okay, so there's the restrictions. So this is a natural domain. All right, so you see that um, this is part of the domain, and this is the range. Range is z. Domain is a part of xy. Okay, so for example, catch the graph of this one here. 36 minus 9 square minus 4y squared. All right. So if you square the z, this is actually for z non-negative because you take a square root, right? But if you square this, you get this one here. So you get rid of the square root, you get this, and you recognize this as an ellipsoid. Okay. So this is the uh, upper one half of the ellipsoid. Okay, so we sketch the graph of y squared minus x squared. All right, so let's see. That's something that we did using Maple. So this is various kind of, this is equal y squared minus x squared. This is minus 4x cubed y squared. Yeah, various stuff. Okay. So this is more complicated. XY exponent. This is the that we try to plot. Exponent negative x squared plus y squared here. Okay. Various plots. What we tried to do earlier is try to describe level curves. Level curves is the curves by cutting the objects. Z equals constant. Okay, Z equals C. So you get a cut here and see what kind of the shape here you get. You get a level curves. See? So on, if you look at the maps of a globe or whatever an area, you see from the top, this is something like this. This is a contour map. So contour is a curves with the same height, same same altitude. So this is the altitude. For example, this is 7,000 feet. This is 8,000 feet, and then whatever there, 9,000 feet maybe. Okay, so the same height. So this is contour map of z equals y squared minus x squared here. This is the shape of contour map of this. It's contour map of this. Okay, so you can get various kind of contour map uh, from Maple earlier. Okay, in fact, you can do some variations of this. Show you the Maple. Let's see, where's that Maple? Uh, one. Well, let's drag this slightly bigger. All right, so that's the surface with contour. So this is a contour. So this is a contour from the top. All right. You can set the contour here. This is like the cuts contour on the top. You see those. Okay. So this is the cuts of the surface. Right. And you also can do whatever here. This is style, surface. Surface. All right, so you can try to explore using Maple Mathematica. Okay. Here's the contour. This is what you see from the top. This is the contour. Okay. If the This is an isotherm saying that 2 points on this curve here uh, represent two locations with the same temperature. For example, isotherm term is the temperature, thermal. Okay, so that's something that we still can do visualizations of this. All right, but with more variables like this one. So when x, y, and z are the free variables, and you gotta have another letter for to represent the range. Okay, and we ran out of space to plug the functions. Okay, because we only have three axes, x, y, z. We don't have the extra axis, so you won't be able to visualize that. But one of the thing we can visualize, at least the lateral curves. Okay, this is the plot for the when the value is constant. So say this is the level sets. Okay, so let's do some more examples of this. Sketch the graph, determine the domain. All right, so let's find domain. Okay, for example, domain of just thank you. Okay. So usually we write this down as c equals f of x or y. Okay, and xy is some b. This is domain. The range is c. Okay, and we represent this as x, y, z, and domain is some part of this. Okay, and the value of the point. So this is f of this is x, y. And I usually write this down in a more this is a surface. Uh, This is projection. So this is D, for example. The domain. This is the plane, not the plane, the surface of, okay. So that's usually the generic picture of the function of two variables. Okay. So let's find domain. Let's see. Where is that thing? Themes, this negative. To find the domain for this one here. The function, find the domain. So from this expression, you see that you need to have x squared y squared plus z squared to be positive, right? So where you have this one here. All right, so this is a uh, oh, this is three variables. All right, so this is three variables. Okay. So you have these conditions. All right, so let's see. This can be zero. So the only thing, because this is square of each, so each of this is a non-negative, cannot be negative. So the only possible things when x squared plus y squared plus z squared equals zero, except when, okay, and this gives you x equals y equals z equals zero. Okay, so the domain here is what I call this is natural domain, is everything except, I should say this, every is every point except 0, 0. So those are the what call the natural domain. Okay. All right. So let's do this one. Z ln xy. So, there's no restriction on Z. Okay. But here there's some restriction XY. So XY should be positive. Okay. So then this tells you that X and Y must be of the same sign. X positive, Y positive, or X negative, Y negative. Okay. So this is uh, so this tells you that X, Y must be the same sign. Positive, positive, or negative, negative. Okay. So the domain here would be consists of two parts. So set of X, Y, Z, where X positive and Y is positive, plus, let's write it down here. Set of X, Y, Z, when X negative and Y is also negative. Okay. There's no restriction on Z. So this is natural domain. Okay. Say another example. So let's go back to say just this one. Uh, right, so let's do this one here. Okay, find domain, natural domain. So from this one, the restriction is X must be, because what's inside the Ln must be positive. So then X must be bigger than 1. Okay. And here on the denominator, so you have X squared should be uh, bigger than Y. Okay. But this cannot be 0 also. So this must be strict there. Okay. So then this tells you that X squared is bigger than Y squared. So that means if you draw the picture, this X equals Y squared. That's a parabola. Okay. And X squared is bigger than this one, meaning that uh, just plot a function is 1, 0 inside or outside this one. If you plot 1, 0, this is 1, 0 is that makes the statement correct. Okay, so the area should be here. So outside this one. All right. But then X must be to the right of 1. Okay, so let's see. This is 1, 1. Okay, and there is 1. All right, so what is the domain? The domain should be this part. Yeah. The intersection of this. Okay. So the domain is the set of xy, where that x squared must be bigger than y, and x must be bigger than 1. Okay, so that's the natural domain for this function. All right, questions? Easy so far? Okay, so look at this one. Okay, so this shows you a contour map. So contour is a location of points which has the same, say, altitude, same height. Okay, so suppose this is a shows you a contour from a mountain. Okay, let's see what's the story behind this one. So this is the story for a mountain 3,000 feet high. What is special about the path from to the top labeled AC? What's special about BC? Okay, so what could make good estimates of total length of path AC and path BC? Okay, so let's see. So this is uh, so one walks from a point A to C. If you look at the contour, this is 0, 500,000, 5,100, and this is probably going down, and this is the highest maybe, and this is the again this is going down. So this is going up, 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 and this is going down. So you see, uh, from from A is going up, sloping with this distance. You can see this is 3,000 feet, this distance. So from here to here, this is 3,000 feet, and this is another 3,000 feet. So 6,000 feet from A to C. And it rises up to, this is 2,000. This is 2,500. This is 3,000. So during, this is around 6,000 feet. About, say, about 6,000 feet. And you rise up by 3,000 feet from 0 to 3,000. Okay, so say slope 1. On the other hand, from C to B, descending from C to B, it's only, well, this is maybe just one half of this, maybe just 500, 1,500 feet. Maybe. Just look at this one. Oh, sorry. This one, this 3,001 to 3,000, this must be 1,000 feet. And maybe this is just 500, sorry. So what does it mean? In 500 feet, walking 500 feet, you drop 3,000 feet, meaning this is much steeper than this one. Okay, from, from C to B, it's much steeper. Then from C to A, okay. So this is what the graph tells you about. Okay. So for example, this is exercise using computer aided, what is ACE? Don't remember. But this is the stuff that you should try to attempt to plot in using Maple Mathematica. There. Okay. Any questions? All right. So let's now do derivatives. Just say give you introduction to derivatives of two variable functions. All right. So say, so what is derivative? Well, the derivative is rather strange here because let's see, if you try to say uh, plus, so let's see, minus, okay, but then, hey, this is a factor. Hmm, so this is just a copy the procedure of, well, copy procedure is this one. If f is one variable, then derivative is this. Oh, so different in x, slightly move the x plus h, subtract of fx, see the difference, divide by this h, and take the limit as h goes to, gets smaller and smaller, goes to zero. Okay? So we would like to emulate, copy this method here. Is that possible? All right. So the thing here is that, well, sorry. So x in the domain should be somehow moved, uh, translated by h. X is a number. So somehow x plus h must be there. So h must be a factor. All right. So subtract xy. Okay. But then you have to divide by h. Okay. That is the problem. So because you have to get a half division by a factor. This is not defined. Okay. So this operations here is simply not good. Okay. So we cannot just copy this definition to two variables. No. for functions or 2 or 3 variables. So we just pretend f to be 1 variables and 1 fixed. Yes. Pretend 1 variables with fixing uh, another variable. Okay. So here fix x or fx y not. Okay. So fix x here. Here we fix. Okay. So we pretend this is the 1 variable. Then as 1 variables, you can do the derivative. Okay. This is what we call a partial derivative. All right, so we stop here. Okay. I have a complete video for this chapter 12, but in Bahasa Indonesia, I'll give you the playlist. So it's a short video, so about 10 minutes each. But a few 16 or so few. No, there's about more than 20 videos, short videos for this one. All right, we'll stop here and then have the on Thursday the problem sessions with the Kemal. Okay, stop here, stop right.